Q6686. During climbing flight using a turbocharged airplane, the manifold pressure will remain approximately constant until the A. Engine's critical altitude is reached. B. Airplane's service ceiling is reached. C. Wastegate is fully open and the turbine is operating at minimum speed. The correct answer is A. Turbocharging operation. A turbocharged engine uses a turbocharger to increase the density of the incoming air, allowing the engine to produce more power at higher altitudes where the air is thinner. The turbocharger consists of a turbine driven by exhaust gases and a compressor that pressurizes the intake air. The compressor provides the boosted air to the engine, increasing its performance. Manifold pressure. Manifold pressure is a measure of the pressure of the air-fuel mixture entering the engine's cylinders. It is controlled by the turbocharger and varies with engine power settings and altitude. During climbing flight, the throttle is usually set to a high power setting, and the pilot aims to maintain a constant manifold pressure to ensure consistent engine performance. Turbocharger limitations. As the aircraft climbs to higher altitudes, the ambient air density decreases. The turbocharger compensates for this by increasing the boost pressure, maintaining a constant manifold pressure. However, there is a limit to the turbocharger's effectiveness. At a certain altitude, known as the critical altitude, the turbocharger can no longer maintain the desired manifold pressure, and the pressure starts to decline. Constant manifold pressure. Until the critical altitude is reached, the turbocharger is able to deliver enough boost to maintain the desired manifold pressure, and the pressure remains approximately constant. This allows the engine to maintain consistent power output and performance during climbing flight. In summary, during climbing flight in a turbocharged airplane, the manifold pressure will remain approximately constant until the engine's critical altitude is reached. Beyond that altitude, the turbocharger's effectiveness diminishes and the manifold pressure starts to decrease. It is important for pilots to be aware of the critical altitude to ensure optimal engine performance during climbs at higher altitudes. 6684. What energy source is used to drive the turbine of a turbocharged airplane? A. Ignition system. B. Engine compressor. C. Engine exhaust gases. The correct answer is C. Turbocharger system. A turbocharger is a device that increases the density of the incoming air to an engine by compressing it. It consists of two main components, a turbine and a compressor. The turbine is driven by the engine's exhaust gases, while the compressor pressurizes the intake air. Engine exhaust gases. The engine exhaust gases, which are a byproduct of the combustion process, contain a significant amount of energy. These high-temperature and high-pressure gases are directed through the turbine section of the turbocharger. Turbine operation. As the exhaust gases flow through the turbine, they strike the turbine blades, causing them to rotate. The turbine is connected to the compressor through a common shaft, so the rotation of the turbine drives the compressor. Energy transfer. The kinetic energy of the exhaust gases is converted into mechanical energy as they pass through the turbine. This mechanical energy is then used to drive the compressor, which compresses the incoming air before it enters the engine cylinders. The compressed air allows for increased fuel delivery, resulting in improved engine performance. Power boost. By compressing the intake air, the turbocharger increases the density of the air entering the engine. This allows the engine to burn more fuel and generate more power, resulting in increased performance, especially at higher altitudes where the air density is lower. Therefore, in a turbocharged airplane, the turbine of the turbocharger is driven by the engine exhaust gases. The energy contained in the exhaust gases is harnessed to power the turbine, which in turn drives the compressor, providing the engine with pressurized air for improved performance. 6653. Detonation in an aircraft engine is most likely to occur whenever the A. Fuel/air ratio is such that the mixture burns extremely slow. B. Engine is operated under conditions which cause the fuel mixture to burn instantaneously. C. Fuel being used is of a higher grade than recommended by the engine manufacturer. The correct answer is B. Detonation. Detonation is an abnormal combustion phenomenon that occurs when the fuel mixture in an engine ignites almost simultaneously, rather than in a controlled manner. It results in a rapid, uncontrolled burning of the air-fuel mixture, often accompanied by a knocking or pinging sound. Instantaneous fuel mixture ignition. Detonation is most likely to occur when the engine is operated under conditions that cause the fuel mixture to burn instantaneously. This means that the ignition of the fuel mixture happens too quickly, resulting in a sudden and uncontrolled release of energy. Causes of instantaneous fuel mixture ignition. There are several factors that can contribute to instantaneous fuel mixture ignition and increase the likelihood of detonation. A. Hot spots. If there are hot spots within the combustion chamber, such as carbon deposits or glowing spark plug electrodes, they can act as ignition sources and cause the fuel mixture to ignite instantaneously. B. Excessive cylinder pressure. High cylinder pressures, often caused by factors like high compression ratios or high manifold pressures, can lead to instantaneous fuel mixture ignition. When the pressure is too high, it can cause the mixture to ignite before the spark plug fires. C. Lean fuel mixture. A fuel mixture that is too lean, in excess of air compared to fuel, can also contribute to detonation. A lean mixture burns faster and can lead to instantaneous ignition, increasing the risk of detonation. Detonation consequences. Detonation is a destructive process that can lead to significant engine damage. The sudden and uncontrolled burning of the fuel mixture generates excessive pressures and temperatures within the combustion chamber. This can result in engine knocking, increased stress on engine components, and potentially severe engine damage, such as broken pistons, bent valves, or cracked cylinder heads. Therefore, in an aircraft engine, detonation is most likely to occur when the engine is operated under conditions that cause the fuel mixture to burn instantaneously. Factors such as hot spots, excessive cylinder pressure, and lean fuel mixtures can contribute to this phenomenon. It is essential to operate the engine within recommended parameters to prevent detonation and ensure safe and efficient engine performance. 6654. Detonation occurs at high power settings when the A. Fuel mixture explodes instead of burning progressively and evenly. B. Fuel mixture is ignited too early by red-hot carbon deposits in the cylinder. C. Intake valve opens before the previous charge of fuel has finished burning in the cylinder. The correct answer is A. Detonation. Detonation is an abnormal combustion phenomenon that occurs when the fuel mixture in an engine ignites almost simultaneously, resulting in a rapid and uncontrolled burning of the air-fuel mixture. It is characterized by a sharp, knocking sound and can lead to engine damage if not addressed. Exploding fuel mixture. Detonation occurs when the fuel mixture explodes instead of burning progressively and evenly. In a normal combustion process, the fuel mixture should burn in a controlled and even manner, with the flame front spreading smoothly across the combustion chamber. However, in detonation, the fuel mixture detonates or explodes, causing a rapid pressure rise within the combustion chamber. High power settings. Detonation is more likely to occur at high power settings, where the engine is producing significant power output. At higher power settings, the combustion process becomes more demanding, and the risk of detonation increases. Factors contributing to detonation. Several factors can contribute to detonation at high power settings. A. Hot spots. Hot spots within the combustion chamber, such as carbon deposits or glowing spark plug electrodes, can act as localized ignition sources. If the fuel mixture encounters these hot spots, it can ignite prematurely and result in detonation. B. High cylinder temperatures. High cylinder temperatures, often caused by factors like advanced ignition timing or lean fuel mixtures, can promote the occurrence of detonation. When the temperature is excessively high, it can cause the fuel mixture to ignite more rapidly and explosively. C. Incorrect spark timing. Improper ignition timing, such as overly advanced timing, can cause the fuel mixture to ignite too early, leading to detonation. Consequences of detonation. Detonation can cause severe stress and damage to engine components. The rapid and uncontrolled pressure rise puts excessive strain on pistons, connecting rods, cylinder heads, and other engine parts. Prolonged detonation can lead to piston damage, bent valves, cracked cylinder heads, and other serious engine failures. Therefore, at high power settings, detonation occurs when the fuel mixture explodes instead of burning progressively and evenly. Factors such as hot spots, high cylinder temperatures, and incorrect ignition timing can contribute to detonation. It is crucial to operate the engine within recommended parameters and address any issues that may lead to detonation to ensure safe and reliable engine performance. 7295. Detonation occurs in a reciprocating aircraft engine when A. The spark plugs are fouled or shorted out or the wiring is defective. B. Hot spots in the combustion chamber ignite the fuel/air mixture in advance of normal ignition. C. The unburned charge in the cylinders explodes instead of burning normally. The correct answer is C. Detonation. Detonation is an abnormal combustion phenomenon that occurs when the air-fuel mixture in the engine's cylinders explodes rather than burning normally. It leads to a rapid and uncontrolled release of energy, often accompanied by knocking or pinging sounds. Unburned charge. Detonation occurs when the unburned charge in the cylinders explodes instead of burning normally. During the combustion process, the air-fuel mixture is ignited by the spark plugs, and it should burn progressively and evenly, generating the desired power output. However, in the case of detonation, the unburned charge ignites in an uncontrolled manner, leading to a rapid pressure rise and the characteristic knocking sound. Factors contributing to detonation. Several factors can contribute to the occurrence of detonation. A. High cylinder temperatures. High cylinder temperatures can increase the likelihood of detonation. When the cylinder temperatures are excessive, the unburned charge can ignite prematurely due to the high-temperature environment. B. High compression ratios. Engines with high compression ratios are more prone to detonation. Higher compression ratios lead to increased cylinder pressures, which can cause the unburned charge to ignite in an explosive manner. C. Lean fuel mixture. A lean fuel mixture, where the ratio of air to fuel is higher than optimal, can also contribute to detonation. A lean mixture burns faster and can lead to uncontrolled ignition and detonation. D. Ignition timing. Incorrect ignition timing, such as overly advanced timing, can cause the unburned charge to ignite too early, leading to detonation. Consequences of detonation. Detonation can cause severe damage to engine components. The rapid pressure rise puts excessive stress on pistons, connecting rods, cylinder heads, and other engine parts. Prolonged detonation can result in piston damage, bent valves, cracked cylinder heads, and other critical engine failures. Therefore, in a reciprocating aircraft engine, detonation occurs when the unburned charge in the cylinders explodes instead of burning normally. Factors such as high cylinder temperatures, high compression ratios, lean fuel mixtures, and incorrect ignition timing can contribute to detonation. It is essential to monitor and maintain the engine within recommended operating parameters to prevent detonation and ensure safe and reliable engine performance.